So this is a joint work with my co-worker Simon Tungvadseth, which is also a PhD candidate at the same university, and it's also done together with our supervisors Henrik Andersson and Magnus Stålhanne. And the starting point for this work was based on our previous work in our PhDs, where we wanted to create a hybrid method from the math heuristics developed by Simon and the branch and cut methods developed by myself. And the reason for this is that, at least to the best of our knowledge, the math heuristics from Vadseth et al. They have obtained or have most of the best known solutions on the benchmark instances, at least for the large set. And the branch and cut methods developed by myself and my supervisors are also the one, as far as we know, with the best dual bound at the root node, representing the tightest formulation within the branch and cut framework. So we wanted to combine these and see if we could kind of enhance them by combining these two methods, or three, so to speak. So yeah, because the motivation there is that, yeah, to get a good primal bound in the branch and cut could improve the branch and cut method itself in two ways, either by allowing earlier pruning of the branch and bound tree, or allowing for better variable fixing during the solution process of the commercial solver we used. And then again, if the branch and cut method finds a better feasible solution during the branch and bound, it's also interesting to see if the improvement methods of these math heuristics can further improve this feasible solution. So we wanted to make a framework there where we combine these methods, and then we had an additional goal to try to further improve this hybrid method by enhancing each individual component. So the outline of the method looks like this, where we start with constructing a feasible solution, which is the main component is there taken from Simon's work from 2021, and then this feasible, like the best feasible solution we can find here, is fed into improvement heuristic, which is basically an MILP that tries to improve or modify the routes in the solution in such a way that we improve the solution. And then once this method converges or reaches a maximum number of iterations, the solution is used to initialize the branch and cut method. And the branch and cut method runs either to determine everything criteria is met, or it finds a new best feasible solution. And if it does, it feeds it back to the improvement heuristic, which tries to improve it. And if it does, it passes back to the branch and cut, and so on it goes until it either proves optimality or it reaches the time limit, and then it will terminate. So let's just go through each and one of these to quickly see how they work. My main focus will be on the improvement heuristic, but let's first look quickly on how we construct the feasible solutions. So here we start by generating a set of promising routes using two heuristics, and then we solve a problem defined by a Pathflow model that selects the best set of feasible routes to serve the customers and determines the delivered quantity to each of these customers. So this would be the same as a restricted master problem in a column generation framework, but we choose to refer to here as a Pathflow model because we're not really doing column generation. We're just generating them initially here heuristically, and then we solve this Pathflow model to obtain a feasible solution. And this is solved by a Gurobi, and we terminate this either if it manages to solve it to optimality or if it reaches some time limits. Yes. So let's have a quick look at the two heuristics we use to generate routes. The first one is the same presented in the previous work of Vadseth et al., where we create the giant tour, which is a TSP solution of the graph consisting of all customers and all arcs between these customers. And then we assigned the delivered quantities to the customers, predetermined to be a certain percentage of each customer's inventory capacity. And we start with 80%. And then we convert this giant tour with corresponding delivered quantities to a VRP solution for each period using the splitting algorithm of Vidal. And then we perform 16 iterations of step 2 and 3 here for decreasing percentages P with decrements of 2.5. And that gives us an initial route pool that is used in this Pathflow formulation to get a feasible solution. And then we, for the competition, developed a second heuristic to try to diversify or get more diverse set of routes, which is quite simple and it's very fast. And it's assigning delivered quantities to the customers such that as many customers as possible with the same demand pattern are visited in the same periods. And here we mean with demand pattern, customers that would be visited in the same periods if you apply a just-in-time delivery policy and an order up to policy. So that you would visit as soon, when they're empty and fill up maximum, fill up as much as you can once you visit. Then trying to kind of group together customers that will run out of products in the same period somehow, hoping that this would generate some different routes. And then once we have such a feasible solution, then disregarding vehicle capacities, and the routing, we solve a VRP instance for each time period with the open source hybrid genetic search algorithm from Vidal, which we have seen a lot already. And then this gives us another set of feasible routes that we ultimately put into this Pathflow model and solve it to get, let's say, a promising feasible solution. And then we move on to the improvement part of the heuristic, which aims to improve the solution found by the constructive heuristic. And here we formulate a Pathflow inspired model that can modify the routes found by the constructive heuristic if the modification is strictly improving the objective function value. So it's also selecting a set of routes, but we also decide whether to insert a node into the route or not. So we can, in that sense, modify the routes. And a key property of this model is that we have formulated it in such a way that we have an exact evaluation of the cost of the route modifications, so that any proposed modification of this model will also be strictly improving for the full problem. So let's just look at it like with an example a bit, how it's done. So from the constructed heuristic, we start out with a pool of routes where we choose a set of routes or a feasible set of routes. And if we look at this example for here, where we have a route consisting of 3 customers, we go from the depot to customer 3, 8, 2, and 0. We then, let's say, rearrange the cost structure somewhat to accommodate our proposed formulation. So we denote a cost parameter to insert a node or a customer into the route, which is calculated as the cost of going from, in this case, 0 to 3 and from 3 to 8, minus the cost of going from 0 to 8. So it's kind of the marginal cost of inserting that node into the route, and we do that for all the customers that were originally in the route, and we then calculate, let's say, a base cost on this route that takes the total cost of the route minus each of these marginal, or the sum of these marginal costs. So then we end up with a cost of using the route of being the sum of these arcs. And then you see that if we choose to use this route in the model and insert all of these customers, we see here that all these terms here are canceled out, and we end up with the original cost of the full route, which is 0, 3 to 3, 8, 3 to 8, 8 to 2, 8 to 2, and 2 to 0. And since we then choose which nodes to insert in the route, we can then decide to remove a customer from the route by setting this variable to 0. And then we have an exact cost evaluation of that removal. But to maintain this structure and have this property of an exact evaluation, if we go back here, we can't remove 2 customers in a row, because it would then break down this cost structure. So we impose constraints that make sure that we can't remove 2 customers in a row from a route, but we can remove every other. So we can remove up to half of the customers in a route with this exact evaluation. And we also accommodate insertion of customers that was not originally in the route, and that's also fairly easy. Then we have this marginal cost of inserting a customer to a route. But let's see. Yeah. There. So in this case, we have a customer that was not originally in the route that can be positioned in any of the spaces or between any pairs of customer or nodes of the route. And then to keep this cost structure, we ensure that they can only, or that the preceding and the node after the inserted node has to be 1, and we cannot insert more than 1 node between 2 existing nodes of a route to maintain this cost structure that we have defined. And this, if we look here at the example route from the depot to 3 to 8 to 0, we can obtain quite a diverse set of routes from these simple modifications. And the advantage is also that it's the MILP is able to find, let's say, swaps between periods, which is very hard to evaluate. Or not very hard, but it's more complicated to evaluate. And here you can see that we use the removal, or the model has used the removal on customer 2 and 3, and here it's removed customer 2, and here it's removed customer 3. Here it's inserted node, and we can obtain quite a lot of different routes from these simple modifications. And we've also added the possibility of adding clusters to accommodate the insertion of more nodes, because that's a bit of a drawback, that is very simple, these changes we're allowed to do. So we tried to accommodate the insertion of clusters in order to insert more nodes, and then we also impose a restriction that if let's say a customer that is part of a cluster cannot be also inserted somewhere else. So we ensure that a single customer can only be inserted one place. So just to sum up quickly, we have then this model allow for 3 possible modification of routes. It's customer removals, it's customer insertions, and it's cluster insertions. And then this is run repeatedly for some iterations until convergence or some max number of iterations is reached. And then we use one mechanism to expand the route pool once again, and then we repeat this iterative solving of this milk. But yeah, I don't think we have time to go into that mechanism now. And then once we have obtained this improved feasible solution, we pass it on to the branch and cut method, which is a slight modifications from the one that was recently published. So we use the customer schedule formulation that was recently proposed. And a customer schedule, it is or a customer schedule for a given customer contains the information of which periods the customer is visited and the delivered quantity in each of these periods. So the advantage of the modified version is that it drastically reduces the number of customer schedules needed, but at the cost of potentially weaker impact on the dual bound when branching. I'll just quickly point it out. It's not, I won't go into the details, but this proposed formulation is basically a Danzig-Wolff reformulation of this part here of the feasible region. So I guess most of you will recognize the inventory balance and the inventory levels, or the limitations on the inventory levels, and the maximum level inventory policy, and enforcing visits if you deliver something. So we enumerate all extreme points of this feasible region, and substitute the original variables with convex combination of these customer schedules. And then I just quickly point out for those that are interested in the paper that the modification regards the substitution of the visiting variables. So this equality sign here makes requires us to generate customer schedules where you visit but you don't deliver anything, in order to have this to not cut away any feasible regions when you make these convex combinations. But if we instead change that to a greater than or equal to sign, we eliminate all these schedules, because then it's just a lower bound on the visiting variables. So the dual bound in the root node will remain just as strong, but the up branch on visiting node might become weaker. So that was changed down to accommodate the largest instances better, because the A matrix can become quite large with enumerating all these patterns, and then the idea there is that it hopefully speeds up each or the solution or the solving of each node in the branch and bound tree. And yeah, let's just have a quick look on the results. So these are for each instance class. So we have the small set on top here, like the high and low inventory cost for 3 periods and high and low inventory costs for 6 periods. And then finally high and low inventory for the large set. And we see the gaps are fairly good, even though we tailored everything to focus on primal bounds here. Even the branch and cut method was tailored to prioritize good primal solutions. But you see that does use quite a lot of time, and we find 278 instances, or we proved 278 instances to be optimal, even though we tailored it to focus on primal bounds. And what stands out is the gap here on the large set, and that's just a result of reaching the time limit before we get to the branch and cut method, so we don't obtain actually a lower bound there. And as was I'm not sure it was mentioned, but we won the competition that we were very pleased with, and it's always interesting to have a more detailed look on or comparing the results between the teams in more detail, because in this field it's rarely the case that you're best on all subsets of instances. So if we have a look on the average percent from the best known solution per instance class across the solvers, we see that our solver is outperforming the others on the large sets, but not so much on the small set actually. So here we find decent solutions, but we're not among the best, which is quite interesting. And just to quickly look also, if we look across customers here, we see this kind of the same thing, that we perform, or the proposed method here performs significantly better on the larger instances, so for 50, 100, and 200 customers. And yeah, let's also have a quick look on the number of best known solutions found. So here the BKS is the best number of best known solutions for each instance cluster, and then BKS star is the number of instances where the solver has the best known solution alone, so that it's the only solver that obtained that best known solution. So again, we see that our method is really doing well on the large set, and yeah, let's say decent on the smaller set. But in some we do find best known solutions on 722 out of 1,038 instances, and 253 of them we have the sole best solution. So we are very pleased with the results of our methods. And yeah, if you have any questions, thank you for your attention.